Hello and welcome to a video on circle theorems. And what we're going to do in this video is we're going to try and prove some of the circle theorems. So hopefully you know what they are by now, or at least what most of them are. But I always think it's good practice to understand where these circle theorems come from. So we're going to go through some of them in this video and then some more of them in the next video. And I'm just going to go through them one by one and try to prove the statement that's given. And for all of these proofs, I encourage you to pause the video before I go through it, just because I think that's the best way of learning this. So the first one we're going to look at is this one here. So it says the angle in a semicircle is a right angle. And you can see that we've got a semicircle here and we've constructed an angle, and that is a right angle. But what we're saying is that it doesn't matter where we draw our angle in the semicircle, it will always be a right angle. So let me just show you if I were to draw another one. Let's say we go over here and then draw a line from this point back to the edge of our circle, the circumference of our circle. And what we're saying is that this angle that's just been created is also 90 degrees. Okay, so we're going to try and prove that now, and I'm going to use this blank circle to do that. And now the key for most of the proofs is to draw in radii. So that's the first thing I'm going to do. I'm going to draw in a radius that goes from the center of my circle to the edge at this point here. So I've drawn in a radius, and you can see now that if we focus on this triangle at the top here, well, this is a radius, and now I've drawn in another radius. We can see that this is an isosceles triangle. And what do we know about isosceles triangles? Well, the base angles are the same. So let's draw some angles in. So this angle here, let's call that angle A. Well, I know that that angle is the same as this angle because they are the base angles of our isosceles triangle. And now if we focus on the angles, the triangle at the bottom, well, this is also a radius. And notice we've got another isosceles triangle. So this angle here, let's call that angle B. Well, that is going to be the same as this angle here, so we can call that B as well. Now, what is the other thing we know about angles in a triangle? Well, they add up to 180 degrees. So now if I focus on this big triangle, I can add up all of the angles. So this angle here, A, plus angle B, plus this angle here. Now, I don't know what each individual angle is, but that doesn't matter because we're only focused on this big angle. So how can we write an expression for this angle? Well, that's just going to be A plus B. So plus A plus B, and we know that they sum to 180 degrees. And now we can do a bit of simplification. So A plus A, well, that gives us 2A. And then B plus B, well, that gives us 2B. That equals 180 degrees. And now we can divide everything by 2. Let's just bring it down here. That leaves us with A plus B is equal to 180 divided by 2 is 90 degrees. So it doesn't matter that I don't know what each individual angle is. I know that when we sum them together, we get 90 degrees. So that's just proved that this angle here is a right angle. And it doesn't matter where we draw our semicircle or where we draw our angle in our semicircle, this sort of logic will still hold true. So this angle, we've just proved that this angle, A plus B, is always going to be 90 degrees. Okay, the next circle theorem we're going to have a look at is this one here. So it says the angle at the center, which is this angle here, is twice the angle at the circumference. So what we're saying is this is twice as big as this one. So if this is A, this is going to be 2A. Notice both of these angles are formed from the same 2 points on the circumference. So over here, we're saying that this one is 2A, so that's twice as big as this angle here. Now this one does look slightly different because the angles overlap with one another, but it's exactly the same. Notice both the angles are formed from the same 2 points on our circumference. This is the angle at the center, so that is going to be 2A, and this is the angle at the circumference, so that's going to be A. So for this particular one, I'm going to prove it twice just because they look slightly different. So I'm going to try and prove that the angle at the center is always twice the size of the angle at the circumference. So just like before, if we draw in some radii, so this time I'm going to draw a radius from this point here up to the circumference of my circle. So this point is a radius, or this line is a radius. This line is a radius, so we can see that this angle and this angle must be the same because they are base angles of an isosceles triangle. So if I call that one A and I call that one A, and now if I do the same thing with this triangle, so this is obviously a radius. Now we can see that, just choose a different color, this angle and this angle are also the same. So let's call that B and let's call that B. Now, what I'm going to do now is work out the last angle of my triangles. So this angle here, how can we write an expression for that angle? Well, we know that angles in a triangle add to 180. So this is just going to be 180 minus B plus B, or 180 minus 2B. And if we do the same with this angle, well, that's just going to be 180 minus 2A. So 180 minus 2A. Now we can calculate this angle, which is the one we want. So let's choose another different color for this one. Let's choose maroon. So this angle here, what is this angle? Well, this time we know that angles around a point add to 360. So if we take this away from 360, what are we left with? Well, 360 minus 180 minus 180 is just 0. So if we take away negative 2A, well, we're just going to be left with 2A. And if we take away negative 2B, well, we're going to be left with plus 2B. And you can check this. So 180 plus 180 is 360. And then negative 2A minus 2B plus 2A plus 2B is 0. So it's just 360 degrees. So now we can compare this angle that we've just formed with this angle here. So you can see that this angle is A plus B, and this angle here is 2A plus 2B, and we can clearly see that this angle, well, that's just 2 lots of A plus B. 2 lots of A plus B, and we're done. So we have proved that this angle is twice this angle. Okay, let's move on to this one now. So we're going to prove the same thing, but this time our angles are in slightly different positions. So the first thing I'm going to do, as always, is draw in a radius. So I'm going to draw a line from the center up to this point here. So we've got a radius here, and you can see that we've also got a radius here. So we've got this triangle that's formed. So if I call this, let's use different letters. Let's call this C, and let's call this angle C. Now we've also, as well as this triangle that I've just formed, we've also got this triangle here. So this is a radius, this is a radius, so our base angles must also be the same. So this angle here, let's call that D. Well, that's the same as this angle here. So just be careful, it's this angle that cuts through this red line here. So that is also D. So it's not this small angle, but this big angle here. Okay, now let's focus on this angle. Okay, so this obtuse angle that I'm doing in fuchsia. So what is the size of this angle? Well, it's going to be 180 degrees. Take away C, take away C. So that's going to be 180 minus 2C. Okay, now what I'm going to do is, there is a lot to this, so please bear with me, and I appreciate it's getting quite messy, but hopefully with the colours you can interpret what's going on here. So now let's focus on this angle in orange. So that is formed from this triangle. So what is an expression for this angle? Well, it's going to be 180 degrees minus D minus D. So minus 2D. Okay, now we're almost there. Now we can calculate this angle, because this is the one we wanted. That's the angle at the centre. We can calculate this angle because this angle in fuchsia is 180 minus 2C. This angle in orange is 180 minus 2D. But we can see that when we add the orange and the maroon, we get the fuchsia. So we just need to take the orange away from the fuchsia to get the maroon. Okay, and if you've just joined the video, I can appreciate that that doesn't really make much sense, but hopefully in the context of this, it does. So what's this maroon angle going to be? Well, 180 minus 180, that's just 0. So we've got negative 2C minus negative 2D. Well, that's just plus 2D. So that is our angle. But we can just switch the two around. So that is exactly the same as 2d minus 2c. So this is 2d minus 2c. Now the other angle that we're interested in is the angle at the circumference, which is this angle. So this angle is just going to be the blue angle d minus the black angle c. So this maroon one that I'm drawing here, well, that is just going to be d minus c, not minus 2. I don't know why I wrote 2, but that is d minus c. And now hopefully you can see, if I just box these, you can see that this angle is 2 times bigger than this angle. That is 2. If we factor out a 2, we get 2 and then d minus c. So it is 2 times bigger. So, bit of a rigmarole there, but very messy, but hopefully you managed to go along and understand what I was doing. And it doesn't matter where our angles are, as long as we've got angles that subtend the same chord or the same 2 points on our circumference, the angle at the centre will always be twice the angle at the circumference. Okay, so this is the third circle theorem we're going to look at, and it's going to be the last one for this video. And it is angles in the same segment are equal. So notice that these two angles that are formed, they're formed from these 2 points here on the circumference. So if we were to draw a chord that connects these 2 points, then we would have created a segment, which is where the name comes from. But basically it's just these two angles are equal. And now what we're going to do to prove this, we're going to use one of the other circle theorems that we've already proved. Now the first thing I'm going to draw in is, you've guessed it, it's our radius. So I'm going to draw a line from the centre to the circumference here. And I'm going to label this angle E, because I haven't used E yet. Now, if we focus on the green set of lines, we can see that it subtends the circumference here and here. So the angle at the centre is twice the angle at the circumference. We learnt this from our first circle theorem. So this must be a half E. Now, if we focus on the red set of lines, well, that also subtends the circumference at the same 2 points here and here. So this is the angle at the centre. This is the angle at the circumference. So that must also be a half E. And hey presto, these two angles, they're both half E, so they must be the same. So I'm going to leave it there for this video, but we're going to carry this over into the next video, and we're going to have a look at 3 more circle theorems and try to prove them. So hopefully you enjoyed that and that was useful, and I'll see you in the next video. Take care.